3.4, properties of exponential functions. So you already kind of know what they look like, and we want to know how to talk about them. So the first note that we have is on interval. What is an interval? This is an unbroken part of the real number line. So when we say that x belongs to the set of real numbers, that's what we're talking about here as well. And it takes one of the following forms. An interval takes one of the following forms. And I'm going to list them just down. If you need to make 2 columns, you can make 2 columns. If you need to write them all just like one interval and then comma and then another interval, you decide how you do it. But there's a whole bunch of options that we can have. We can say that x belongs to the set of real numbers. That would include the whole real number line from negative infinity to positive infinity. Or we can say that x is less than a, or x is greater than a, and then we would be saying, okay, we're somewhere on this number line. You don't need to draw this. We're saying, okay, here's a, and x is all of these values. Then this would be x is less than a, but not including a. So it would be an open circle at a. And so this is x is less than a, but we can also have x is less than or equal to a. This is x is greater than a, but we can also have x is greater than or equal to a. That would be an interval of numbers, an unbroken part of the real number line. There are more options. We could have x is in between 2 numbers. So we could say it's greater than a, but at the same time it's less than b. So an example of that would be, let's say your number is in between 2 and 4, let's say, exclusive of 2 and 4. You could have this the other way, you could say that it's in between or equal to a and b, so then it would be inclusive of a and b. So it could be anything in between a and b, and it could be a, and it could be b. And then we have a couple of different ones where you can include the upper boundary, but not the lower boundary. And then, of course, you can include the lower boundary, but not the upper boundary. And these are all dependent upon this. This is where a and b are real numbers and a is less than b, or b is greater than a. So I always think about intervals numerically from left to right, from lower number to bigger number. Okay, then just to review, we have this exponential equation here, y equals ab to the power of x. Here's all the pieces of that. A is your initial amount. B is your base, which is the repeated factor. Or you could have that as your growth / decay factor. So if it's greater than 1, it's a growth factor. If it's in between 0 and 1, it's a decay factor. And then we have our exponent, which tells how many factors there are. How many times the base is repeated. So how many factors of b are there? Again, the base determines whether it is growth or decay. So, let's head for example 1. Example 1, we are to analyze the graph of an exponential function. So we're going to graph this exponential function, and then we're going to figure out what is the domain, what is the range, what are the x and y intercepts if they exist. We're going to figure out where this function is increasing or decreasing and where it has an asymptote. So the function is there for us, y equals 4 times 1/2 to the power of x. So it's an exponential function. That means the variable is in the exponent. Is this going to be growth or decay? Growth or decay? It's going to be decay because our repeated factor is less than 1, right? Basically, you're going to be getting the number 4, and you're going to multiply it by 1/2. So you're essentially cutting it in 2 every single time you add another factor. So it's going to get smaller and smaller and smaller and smaller and smaller. This is actually our half-life situation, right? We're starting with 4 of something, and then we're cutting it in half each time. Now to graph it, because it's not attached to a real-world situation, we can actually use exponents that are positive and negative. So in our table of values, you've got an x column and a y column, and we're going to take values of x from -2 to +2. Okay, so that's our exponent. So we have 4 times 1/2 to the power of, we're going to start with -2. Okay, we have done enough practice with this. I'll do 1 off to the side, but then we're really just going to fill in our table. So if I sub in -2 for my exponent, a negative exponent causes me to flip my fraction here, use the reciprocal, and then a positive exponent. So I'm going to be having 4 times 2, and then I use a positive exponent of the power of 2. So I have 2 squared, which is 4, times 2, which is 16. So the corresponding y value for an x value of -2 is 16. And then the rest of the chart is really easy to do because we know we're going to be multiplying every value by another factor of 1/2. So after 16 should come 8. After 8 should come 4. That's a good one to double check because anything to the power of 0 is 1. So I should end up with 4 times 1, which is 4. Again, cut the next one in half, cut the next one in half. And I mean, we could, if you have room in your chart, you can keep going. You could do to the x with a value of 3, x with a value of 4, and really all you'd be doing is cutting your y value in half, cutting your y value in half again. And now this is a good amount of information to help us graph this function. You guys have a perfectly nice little graph there. So you're going to draw your vertical axis and your horizontal axis. And you want a little bit of space to the left of your vertical axis too, just so you're aware, because we used x values of -1 and -2. So you're going to have something out there. 1, 2, 3, 4. Good enough. And our highest value is 16, so I might go up to 20 on my vertical axis. So go ahead and draw that all beautiful on yours using reasonable scale. and then go ahead and plot your points and check up on the board when you're done. Once you have your points drawn, you can draw a smooth curve through those points. And label your graph. Y equals 4 times 1/2 to the power of x. And once we're at this point, we can start to have a discussion about the domain and range. Are there any restrictions on the domain? Any x values that I'm not allowed to put into this function? Like if I put in x equals -10, could I still calculate a value? Yeah, it'd be a really big value. What about x equaled -1,000,000? Yeah, be a super huge value.
You can put in any excess real numbers.
Any x belonging to the set of real numbers.
But why does it always be positive? Why
Okay.
does it always be equal to some zero?
Awesome. So y is restricted to the positive numbers. So our range, y again, belongs to the set of real numbers, such that y is greater than 0. Will it ever reach 0?
No. That would get pretty close. You could probably round it to 0.
So you can always cut something in half, and you can keep on cutting in half, and you will never, ever, ever get to 0. So this will go infinitely along this x-axis, but it will never touch it or cross it. So what does that tell us about the x-intercepts? Is there going to be an x-intercept? No, certainly not going this way because it's going up, 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 and not this way either because cutting something in half, it will never reach 0. So no x-int. What about a y-intercept?
Intercepts at 4.
Y-intercept of 4. And if you want to, you can put a little note of where does a y-intercept occur. It occurs where x equals 0.
Is it possible for it to occur anywhere else?
Nope.
Okay.
But it's helpful to remember that if you did need to find out and you didn't have your graph, all you would need to do is throw a 0 in there. Anything to the power of 0 is 1, so this is going to indicate your y-intercept. What else do we need? Intervals of increase and decrease. So we always, for these questions, intervals of increase and decrease. Increase, increasing, and decreasing. We always read the graph from left to right, right? So from negative infinity to positive infinity. What is the function doing? Increasing or decreasing? Is it growing or getting smaller? Come on, folks. Yeah, it's decreasing, right? It's going down continually. So increasing, none or NA. It's decreasing over its whole domain, okay? The graph is falling to the right throughout its domain. So the y values decrease as the x values increase. So this function is decreasing over its whole domain, yeah? X belongs to the set of real numbers, or the whole domain.
So would an interval be like every whole number?
In this case, the interval that we're using to describe where this graph is decreasing is all real numbers, from left to right across the whole number line. But if this graph decided to go up again, then we would have to figure out where does it start to grow up again, and then change our interval. Okay? Is there an asymptote? So an asymptote is a line that the curve gets closer and closer and closer to, but never reaches. Are there any asymptotes here?
Yeah.
There is. What is it?
Well, we're just saying once it starts getting less and less, because then it'd be x greater than 2.
So the asymptote is an actual line that this graph never touches. So we can see as we read from left to right, we're getting closer and closer and closer and closer to y equals 0, but we will never touch it. So our asymptote is y equals 0. That's the line that it will never touch.
I thought asymptote was like the line that gets really close to the line that you don't touch. Like the part of the line.
Yeah, I guess it's just the line that the function gets closer and closer and closer to but never reaches. And since that's the x-axis, then that's our asymptote. Good job. For b, we're going to follow the exact same strategy here. We've got y equals negative 3 to the power of negative x. So this one's going to be a little bit trickier, but we're going to work it the same way. So we've got x values in our table of values and corresponding y value. Okay, let's fill in our table of values. So we're going to take our values of x to be, we'll start with negative 3 this time, negative 2, negative 1, 0, 1, 2, 3. If you have room for all those, go for it. If you don't, you can trim off the bottom and it'll be okay. So here we're going to be using our rules for exponents and for integers, negatives and positives, but we have y equals negative 3 to the power of negative x. So this is actually negative 3 to the power of 3, which is negative 27.
Negative 3 to...
So you got 3 to the power of 3, which is 27, and it's going to be negative. So here, for this...
this is the power of negative 3.
Ah, careful. X is negative 3. So we'd have to the power of negative 3.
Okay.
Right, so that'll be a positive. Next one, we'd have y equals negative 3 to the power of 2. So 3 to the power of 2 is 9. We'd have negative 9. And from there you can probably just follow the pattern. We're dividing by 3. And, uh-oh, do I have a change of sign here? Do I need to go into the positives, you think? Nope. Just follow the rule. And carry on down. Okay, from there you can use that beautiful graph that you have to graph it. Make sure you leave yourself enough room, and notice that in your y column you're dealing with negative numbers, so that should affect where you put your x-axis. And think about your scale for your y-axis. We went down to negative 27, so about 30. Once you have that drawn, you can plot your points and double check the board to see how you're doing. draw a nice smooth curve.
Oh, yeah.
Label our graph. Scroll up. And discuss.
You have to ask your mom for as much money.
Discuss. Domain. Any restriction on the domain? Any x values that I'm not allowed to put in here?
Oh, you're allowed to put all of
X belongs to the set of real numbers. Range. Any y values not included in this function?
it. Any numbers above 0 or above 0. So all numbers are less than 0.
Okay, so all of our y values are less than 0. What else are we looking for? X-intercepts. Are there any x-intercept? No x-int. Y-intercept? There's easy. Y-intercept of -1. Intervals of increasing and decreasing.
Increasing.
It's always increasing, right? Always increasing. So you could say always, or whole domain, or x belongs to a set of real numbers. Is it ever decreasing? None. No intervals of decrease. And asymptote. Same thing. Except this time we're coming toward y equals 0 from the bottom. But either way, that asymptote, that line that is getting closer and closer and closer but never touching the curve, is y equals 0. So an asymptote at y equals 0. Okay, that's just describing the characteristic of functions. So whenever you have a function, you can talk about these things. You can always talk about the domain and range. You can always talk about x and y intercepts. You can always talk about the intervals of increase and decrease. You can always talk about asymptotes. Okay? So we'll get familiar with talking about those key characteristics of a function. Okay, example 2, we have to do the exact opposite this time. Instead of being given an equation and graphing it, we're given a graph, and then we're going to find its equation. So we need to remember the parts of an exponential equation. We've got the initial amount when x is 0. We have the base, that's the multiplier, the factor that gets repeated, and then x is going to be the variable. So what we can do here is we can just consider a few values of x, see what's happening to the function at each of those values, and then determine what our multiplier should be. So we've got x and y in that little table you have there, and we'll consider 0, 1, 2, and 3. And we'll just look at our graph. And what do we see? We see that we have 0, 2, we have 1, 6, we have 2, 18, we have 3, 54. And we know that in an exponential function, by definition, there is a repeated factor. And we can figure out what that is by finding the change in y. So the change here, there should be a common ratio, right? How are we getting from one y value to the next value?
So 3 times.
Each time we have to multiply by 3. Okay, that tells us that 3 is the factor that's getting repeated. Do we know our initial value? Do we know our initial value? The value of the function when x is 0? Pardon? Yeah, so we found out b, which is our repeated factor. That's going to be 3. We found out a, that's our initial value. That's going to be 2. And that's all of the information that we need. If we did not have this point, if we did not have 0, 2, we could still figure it out. And here's how we would do that. So let's say we just knew, I'm going to write the answer first, y equals 2, 3 to the power of x. Okay? That's what this thing would look like. Now, if we did not have this point, if we did not know that the initial value was going to be 2, we could take what we do know, which is y equals a times 3 to the power of x, and we could plug in values that we know. So if we know that the point 1, 6 satisfies the equation, then we could sub those in for x equals 1 and the corresponding y value is 6. And then we could simply divide both sides by 3 and we'd get a equals 2, which is what we got already. Okay, so that's not so difficult to go from a graph to an equation as long as you know that the form of the equation is y equals a b to the power of x. Alright, last example. Example 3, write an exponential equation given its properties. So this time we're told what's happening to a given substance, and then we have to write the equation that would model this situation. So a radioactive sample has a half-life of 3 days, and the initial sample is 200 milligrams. So what do we already know? We know that we're dealing with a half-life situation. So we know that we're going to be using the formula for half-life, which is the amount remaining, dependent on time, is going to be equal to A naught, which means the initial amount. We know that our repeated factor is going to be a half, because we're talking about half-life. We're cutting the amount of this substance in half every 3 days. And time is our exponent. Okay? And we need to indicate then where x is the time, but the time is not measured in days or hours. The time is measured in half-life periods. So where x is the time, comma, measured in half-life periods.
Like you put the exponent like in brackets x divided by, and then how long you figured the last time?
Yes, you could. So yes, if you wanted to talk about, if you wanted your exponent to be measured in days, then we would have to change our exponent to something like t over 3, which is what we're actually going to get to in this example. Okay? Because the half-life period is 3 days.
Oh, yeah.
So yeah, this would be your number of days, t, divided by 3 would give you your number of half-life periods. Okay, so we'll get to that in a second. Here, let's just draw a couple of arrows so that you know what these things mean. This is pronounced A naught. That's just our initial amount. Initial amount. This is our decay factor. And we already indicated that this x is the time measured in half-life periods. Alright, so what are we starting with? How much of this sample, how big is this sample in our example? The initial sample is 200. Okay, so A naught is 200. We're starting with 200. So all we're going to do is sub that in and rewrite what we have. So this expresses A as a function of x, the number of half-lives, but to express it as a function of time measured in days, Now, replace x with t over 3 to express as a function of time, comma, measured in days. So now we'll be able to relate the amount remaining directly to the number of days that have passed. What does that look like? A with respect to t now is equal to 200 times 1/2 to the power of t divided by 3. So now this relates the amount remaining of radioactive material directly to the amount of time that has passed. Okay? And B, now we want to restrict the domain of the function so that the mathematical model fits the situation that it is describing. Basically what that means is you could graph this function for all values of t, from negative infinity to positive infinity, but if we're talking about time measured in days from this initial 200 milligram point, what's true about our domain? T. What's the restriction?
T equals set of real numbers, and t is greater than or equal to 0.
It's going to be greater than or equal to 0. Okay, so our domain is restricted. We could just say for t belonging to the set of real numbers such that t is greater than or equal to 0. Okay, that's the restriction on our domain. And because we have a couple extra seconds, let's graph this thing. We already know that we're starting with 200 milligrams, so I'd probably, I don't know, go up to 250 on my graph and then split it into 5 parts as accurately as I can. That certainly wasn't very good. $50, 100, 150, 200. And our number of days are going, you can just go 1, 2, 3, 4. We know we're going to cut this thing in half, and in half, and in half, and in half. And we'll see what's left. So we're starting at 200. That's our initial amount. And then I know after one half-life period, we'll be down to 100 milligrams. So one half-life period is actually 3 days. So once I'm at the 3, I'm down at 100. Okay? After another 3 days, maybe we'll extend this graph a little bit to give ourselves a better picture. 5, 6, 7. So after another 3 days, we'll be down at 50. And this is what this curve is going to look like. This left tail on the left side of the y-axis doesn't actually exist. But this is going to look something like this. Again, always decreasing, never reaching 0, hypothetically. Restricted. So this is T and A, vertical axis. There's a picture of what that would look like, and whenever we draw a graph, we label the graph with its equation. A with respect to t equals 200, our initial amount, times 1/2 to the power of t divided by 3. There you have it, folks. There is a pretty good summary of notes on page 184 in the key concept section. And that's convenient because you're going to page 185 for your practice problems. Page 185, numbers 1 through 9.
We'll just start the next lesson.